Our final system for this set of videos also is a 3x3. We have dx dt equals negative x plus z, dy dt equals negative y plus z, dz dt equals negative x plus y. I'd like for you to solve this, take it as far as you can, come back, we'll talk about it. I was going to do the work, but I thought it'd be better for you to see it unfold. If you want to skip ahead, go ahead. Equation 1 I'm rewriting as d plus 1 acting on x minus z equals 0. Equation 2, d plus 1 acting on y minus z equals 0. And equation 3, x minus y plus dz equals 0. We're going to use equations 2 and 3 and eliminate y because equation 1 already doesn't have y in it. In order to do that, we're going to take equation 2 and add to it d plus 1 acting on equation 3. Equation 2 is simply d plus 1y minus z is equal to 0. D plus 1 acting on 3 is going to give us a d plus 1 acting on x minus d plus 1y, we see that'll eliminate y's, plus d2 plus d acting on z is equal to 0. The y's are gone, and we've got d plus 1 acting on x plus d2 plus d minus 1 acting on z is equal to 0. I'll call that equation 4. If we compare equation 4 with equation 1, we see that we're going to be able to eliminate x by subtracting equation 1 minus equation 4. Or rather, why don't we say equation 4 minus equation 1, since we already have equation 4 sitting right here. All right, equation 1, negative d plus 1x plus z equals 0. And we see that the x's drop out. We can also see that negative z plus z is going to drop out, and we're left with d2 plus d z is equal to 0. I mean, that really is an auxiliary equation, but we'll write it down. M squared plus m is equal to 0, giving us that m is equal to 0 or negative 1. And so z of t is equal to c1 plus c2e to the negative t. Now we have z, but we're in a bit of a pickle, because while all of the equations contain z's, they also contain x and y, and a dx in an equation is going to be these are problematic. We can't just integrate to get out of that thing. So we're going to go back to equations 1 and 4, and instead of eliminating x's, we're going to eliminate z's. I'm going to rewrite them for us. So we have equation 1, which is d plus 1 acting on x minus z equals 0, and equation 4, which is d plus 1 acting on x plus d2 plus d minus 1 acting on z. I think we're going to be able to eliminate z's by applying d2 plus d minus 1 to equation 1 and adding to that equation 4. And that's going to look like d2 plus d minus 1 acting on d plus 1 x. Just leave it like that. Minus this d2 plus d minus 1 acting on z is equal to 0. And then equation 4 wasn't going to change. So we have d plus 1 acting on x plus d2 plus d minus 1 acting on z equals 0. So the z's drop out. And then if you note what we have, we've got d2 plus d minus 1 acting on d plus 1 acting on x plus d plus 1 acting on x. So the whole thing's acting on x. We can kind of treat this like we're going to factor it. So we have d plus 1 appearing inside the brackets in two different places here. If we essentially factor it out, d plus 1, what we're left with is d2 plus d minus 1 from the first term, and then plus 1 from the second term. And some 1s are going to subtract out. I mean, that's x, it's all acting on x and it equals 0. And now we have d plus 1 d acting on x is equal to 0. And folks, that gives us an auxiliary equation of m plus 1, the quantity squared, times m is equal to 0. And our roots are m equals -1 repeated and m equals 0. X of t will then have a constant term from the m equals 0, but remember, we've already used c1 and c2. So at this point, we need to pick it up with c3. And then we've got plus c4 e to the -t. And because that -1 was repeated, we have plus c5 t e to the -t. You may remember a previous video in which I talked about the constants being connected because the system was coupled. And I'm looking back here at the original equations, and what I see is the first one is dx dt equals -x plus z, and therefore I can use it to connect the constants that we currently have. So taking equation 1, we see it's supposed to be x prime plus x is equal to z, did a slight rearranging. And that's going to give us, for the derivative of x, -c4 e to the -t plus, product rule here, c5 e to the -t minus c5 t e to the -t. So that's the x prime part. Continuing on, plus x is going to be plus c3 plus c4 e to the -t plus c5 t e to the -t. And on the right-hand side, we have that equals z. Z was c1 plus c2 e to the t. -t, excuse me. And we have some things that are going to drop out here. c5 t e to the t shows up in a positive and negative form. c4 e to the -t again subtracts out. And we do have on the left-hand side a c3 and on the right-hand side a c1 for constants. Therefore, we know that c3 is equal to c1. We also have a c5 e to the -t on the left-hand side and a c2 e to the -t on the right-hand side. And so c5 we know is c2. Rewriting x, we now have that x of t in terms of our new constants is c1 plus c4 e to the -t plus c2t e to the -t. How many constants are we expecting overall? I mean, we had c1 and c2 for z, and here we have c1 and c2 and c4, so that's a total of 3 constants. But if we look back, if we consider that we had a d2 plus d minus 1 acting on d plus 1 acting on x, there was a third derivative there, so I am expecting a total of 3 constants. If we're keeping track, now we have x of t, we have z of t. Going back to our original system, I see, we can use either equation 2, nope, not equation 2 because it's got dy, dt, and y in it. Looks like equation 3 is our winner here. dz dt is equal to -x plus y. Well, that means that equation, 3? Gives us that y is equal to dz dt plus x. And I will tell you the result of that is that y of t is equal to c1 plus c4 minus c2 e to the -t plus c2 t e to the -t. Joining that together with what we had for x and z solves the system.